Okay, here comes part two of part two, derivatives as a rate of change. Okay, so in the last example, it was about something being thrown into the air on the planet Mars and coming back down. So in that, the position of the rock that was thrown was height, right? So we're about to look at example 3 on this sheet, and it says a particle. So this is a particle this time, starts by moving to the right along a horizontal line. The graph of its position function is shown in the figure. When is the particle moving to the right? When is it moving to the left? When is it standing still? And sketch a graph of the velocity function. Okay, so this, I've copied down what you guys have on your sheet here. So here is the graph of the position of the particle. So the position is S in meters across time. So it's the first 6 seconds of this particle's movement. And so this time, the positive direction is not up, but to the right is what's been designated as positive. So that means to the left is negative. Okay, so what we look at here is, remember that the slope of a function is its derivative. That's what we're looking at. And the derivative is velocity. So when I look at this, this is a positive slope right here. That means that the velocity is positive. That means that the particle is moving forward in a forward direction. Right here, the velocity is not changing. See, the slope is 0 right there. So the velocity is not changing. That means the particle is standing still. Then we get to here where the velocity, the slope is negative. That means the velocity is negative. So if it's going negative, that means it's going in the negative direction. It's moving the opposite left right here. This is where the slope is 0, meaning the velocity is 0, meaning it's not moving left or right at that time. And then it's positive, the slope is positive, and so the velocity is positive, and it's moving in a forward direction. So that's how you can interpret this position function. Now, it says, when is the particle moving to the right? Well, it's going to be moving to right whenever the slope is positive. So for what values of time? When is it moving to the right? Okay, it's moving to the right. It's moving to the right when the velocity is positive. Well, the velocity is positive when the slope is positive. And the slope is positive right here between t is 0 and 1. Okay. And then it is positive again here when t is 4 and 6. Between 4 and 6 seconds. That's when it's moving to the right. When is it standing still? Well, that's when the velocity is 0. Where's the velocity 0? Where the slope is 0. So that's between 1 and 2 seconds. It's standing still. Between 1 and 2. And also between 3 and 4. All right, and then when is it going negative? It is moving, it's moving to the left whenever it's negative, and it's negative between 2 and 3 seconds. Moving to the left between 2 and 3, oops, and 3 seconds. So that's when it's moving to the left. Okay, so that's how you can answer that part, but then they say, sketch a graph of the velocity function. So here we are. We're going to do it. We're going to sketch a graph of the velocity function. So first, let's say, what is the velocity? Well, if you remember the very first part of this video, the velocity is the derivative of the position function. So the velocity is going to be s prime of t. And if you recall that a derivative is also a limit, is also the slope of a tangent line. Let's interpret the slope here. We've already been looking at the slope to help us get these answers. What is the slope here? Well, this is a line. I can just pick 2 points on this line and calculate the slope, the change in y over the change in x. So let's see. How high did it go for 1 unit of time, right? It went up 1, 2, 3, right 1. The slope of this section of the line is 3. This section right here. The slope, let me see what color I want to give this. The slope here is 3. This has a slope of 3. Right here, it's not changing. It's a flat. Horizontal lines have a slope of 0. Same here. Slope of 0. What is this slope? How up did it go in this space of time? Let's see. It went up 2 units, right? Did I go 1 or 2? Let me see if I did this wrong. No, this went up 2 units, right 2 units, 2 over 2. This has a slope of 1. And how about this part down here? This is a negative slope. It's going to go down 1, 2 units, right 1, negative 2. That is what the slope of this. Well, the velocity is the graph of the velocity is a graph of the slope of this line. So let's graph that. Let's see. Let's do it right underneath. That would be more interesting. Let me do it not beside it. Let's do it right underneath it. So here is the graph of the velocity. Let's see here. Let me make it blue. This will be the velocity, s prime of t. Right here. Okay, so let's see. We have 1, 2, 3, 4, 5, 6. And then we've got our y-axis here, okay. We've got 1, 2, 3, 4, negative 1, negative 2, negative 3. So we said between 1 and 2 seconds, between 0 and 1 seconds, it's up here at 1, 2, 3. It's at 3. Between 0 and 1, it's up here at 3. And then we said between 1 and 2, it's down here at 0. So I'll make that black so we can see that. Between 1 and 2, it's down here at 0. And then also between 3 and 4, it's at 0. And what's it doing between 2 and 3? It's at negative 1, negative 2. It's down here at negative 2. So between 2 and 3, it's down here. And then between 4 and 6, it's got a slope of 1. It's got a slope of 1. So you can put open circles on these guys because there's a little transition. I don't know who belongs to who here, it doesn't matter, but this is a good graph of the velocity of this. So we say, hey, what's the velocity after 5 seconds? Well, that one's easy to see. It's 1 meter per second. That's what we could say right there. Okay, so this is in meters per second. Okay. All right. So that is example 3. Let's just talk about the last example. I'm just going to tell you how to answer this. It says a manufacturer produces bolts of fabric with a fixed width. The cost of producing X yards of this fabric, C, equals to F of X dollars. What is the meaning of the derivative F prime of X, and what are its units? Okay, so this is example 4. What is the meaning of F prime of X? Okay, what did F of X, well, we know that F prime of X is, it's the change in F, which is cost, right, over the change in X, only there's a limit, right, as delta X goes to 0. All right, so there's almost no change in the amount of X. So, what would the units be? Let's answer that part first. What would the units be for this? Well, what are the units of cost? This would it be in money, dollars per X. What does X represent? X represents yards of fabric. So this would be in dollars per yards. That would be the units for F prime of X. It's always a rate for a derivative, okay? And then, so the meaning of the derivative would simply be the rate of change of the production cost with respect to the number of yards of fabric produced. That's what F prime of X. This would be the rate of change, of cost, production cost, with respect to the number of yards of fabric produced. All right, so now they have a second question here. The second question is, in practical terms, what does it mean to say that F prime of 1,000 is 9? F prime of 1,000 is 9. All right, well, what were the units of this? This is $9 per yard. What does F prime? It is the rate of cost for the production cost. So we would say that F prime of 9 means that after after 1,000 yards of material are produced, the production cost is increasing. I say increasing because it's a positive number at a rate of $9 per yard. That's what that means in practical terms. Okay, that is the derivative as a rate of change.